Module 21. Lecture A. MLP Fundamentals. By the end of this lecture, you will be able to explain the structure of Scikit-Learn MLP models in practical terms, fit MLP classifiers and regressors on scaled data, and interpret activation, loss, and prediction behavior for supervised MLPs. Network structure. Perceptron basics. A perceptron is a basic neural network unit that takes several inputs, gives each one a weight, and produces a decision. During training, it adjusts those weights to learn which inputs are most important, such as signals used in spam detection. This ability to learn patterns from examples is a core idea behind neural networks. A perceptron uses weights and a bias to make a classification decision. The weights control how strongly each input feature affects the result, while the bias shifts the decision boundary and helps when inputs are weak. This lets a perceptron separate cases into groups, but more complex tasks usually need multilayer perceptrons that combine many units for richer decisions. In Scikit-Learn multilayer perceptron models, units are organized into layers that pass transformed information forward. Hidden layers learn intermediate features, such as patterns related to house value or increasingly complex image shapes. Although the classifier and regressor interfaces are simple to use, they rely on connected perceptron-like units that adjust weights and biases to reduce prediction errors. Layer structure. A multi-layer perceptron sends input features through hidden layers, where units combine them with learned weights and transformations. The output layer then produces the prediction, such as a numeric value for regression or a class for classification. This layered structure helps the model learn complex patterns in data. In Scikit-Learn, a multilayer perceptron is shaped by how many hidden layers it has and how many units are in each layer. More layers and units increase the model's ability to learn complex patterns, but they also require more data, training time, and regularization to avoid overfitting. Simple datasets usually need only a compact network, while more complex data may benefit from a larger architecture. In a multi-layer perceptron, each layer learns a more refined representation of the data. Early layers turn raw inputs into useful intermediate signals, and later layers combine them into task-specific patterns, such as customer types in a business dataset. Even though Scikit-Learn does not directly reveal these internal patterns, this layered structure can capture complex relationships that simpler models may miss. The network's depth and width must be balanced to reduce overfitting and keep training efficient. Activation functions. Activation functions let neural networks learn patterns that are more complex than simple straight-line relationships. In a multi-layer perceptron, each neuron combines its inputs with weights and biases, then applies an activation function to add non-linearity. Without this step, extra layers would not make the model more powerful. This allows the network to capture interactions in data, such as how income and age together may affect a customer's response to a promotion. In Scikit-Learn multi-layer perceptron models, activation functions shape how hidden layers transform input signals. Rectified linear activation is often efficient because it keeps positive values and suppresses negative ones. Hyperbolic tangent produces centered negative and positive outputs, while logistic activation compresses values between 0 and 1, but can slow learning in deeper networks. In a multi-layer perceptron, hidden layer activation functions and the final output layer have different roles. The hidden activations shape how the model learns internal features, while the output layer changes to match the task. For classification, it produces probabilities or scores, and for regression, it produces continuous values. This distinction helps clarify that activations mainly affect feature learning, not the form of the final prediction. Python code. Activation functions. This script compares hidden activation functions by showing how they transform input signals. The plot highlights the different nonlinear changes each function applies. The script imports NumPy for numerical work with arrays and mathematical operations, and Matplotlib's plotting tools for creating graphs. Together, these libraries provide the basic tools needed for computation and visualization in Python. We create a set of input values for hidden neurons using the NumPy linear spacing function. It generates 200 evenly spaced numbers from -4 to 4, giving a smooth range of signals for comparing how different activation functions respond. The input array is passed through 3 common activation functions. ReLU sets negative values to 0 while keeping positive values, adding nonlinearity. The hyperbolic tangent function maps values between -1 and 1, centered around 0. The logistic function compresses values between 0 and 1, making it useful for binary classification and stable learning. The code verifies that the input signal and the ReLU activation results have the same length, so each input value has a matching output. If they do not match, it raises an error to stop further processing. This check helps prevent problems during later steps, such as plotting or analysis. This reminder focuses on what hidden activation functions do in a multilayer perceptron, rather than on any specific Scikit-Learn version. Hidden activations reshape signals before they reach the output layer, helping the network learn complex patterns. ReLU keeps positive values and turns negative values into 0. tanh centers outputs around 0, and the logistic function compresses outputs between 0 and 1. A plot is created to compare 3 activation functions on the same set of input values. The ReLU, tanh, and logistic outputs are each drawn as separate labeled lines, making it easy to see how each function transforms the input signal. The plot is labeled to make the activation function curves easy to understand. Its title identifies the topic as common hidden layer activation functions, while the axes show neuron input before activation and neuron output after activation. A legend names each curve so viewers can tell the functions apart. The final command displays the completed plot using Matplotlib. It brings together the earlier plotting steps and shows the activation functions on screen, making their comparison visible. This visualization compares how 3 common neural network activation functions transform inputs from -4 to 4. ReLU keeps positive values and turns negative values into 0. tanh centers outputs around 0, and the logistic function compresses outputs between 0 and 1. Plotting these curves shows how each function adds a different nonlinear transformation before the network's output layer. MLP learning mechanics. Forward pass. In a forward pass, a multilayer perceptron sends input data through layers to produce a prediction. Each layer uses learned weights, biases, and activation functions to turn the data into more useful signals. Scaling the input features beforehand keeps computations balanced, so no single feature dominates, and the network can learn more effectively. During the forward pass, hidden layers transform input features into increasingly complex signals, rather than making separate decisions. Scaled inputs, such as medical or retail data, help prevent unit bias and allow the network to learn useful patterns, like risk factors or likely responses to promotions. Once a model is trained, the same inputs and weights will always produce the same output. At the end of a forward pass, the model produces an output suited to the task. In classification, it gives class scores or probabilities used to choose a category, while in regression, it gives a continuous value. This prediction is compared with the correct answer to calculate loss, which guides weight updates during training. Classification loss. Classification loss tells a multilayer perceptron how far its predicted class probabilities are from the true labels. When predictions are close to correct, the loss is small. When they are wrong, the loss is large. The optimizer uses this signal to adjust the network's weights, so its probabilities become more accurate over time. In Scikit-Learn multilayer perceptron classifiers, the classification loss penalizes confident wrong predictions more than uncertain ones. This helps the model learn not just which class to choose, but how confident it should be. During training, each forward pass produces predicted probabilities, and the loss compares them with the true labels to guide weight updates through backpropagation. Scaling input data is important when training a multilayer perceptron, because features with very different ranges can make learning unstable and cause some inputs to dominate. Putting features on similar scales helps the optimizer reduce classification loss more effectively. However, lower training loss alone does not guarantee good performance on new data, so it should be evaluated together with validation results and other metrics. Python code. Classification loss. This example illustrates classification loss in a multilayer perceptron. Scaling helps the optimizer make better use of the loss signal, and the training loss decreases over time. This setup imports the main tools needed to build and evaluate a neural network classifier. NumPy and Matplotlib support numerical work and plotting, while Scikit-Learn provides the breast cancer dataset, tools to split it into training and test sets, and a multi-layer perceptron classifier. A pipeline combines feature standardization with model training, which helps the neural network perform well. Finally, accuracy is used to measure how well the model predicts labels on unseen data. We load Scikit-Learn's breast cancer dataset, a built-in dataset for binary classification. The data is then separated into features, which are the inputs, and labels, which are the outcomes to predict. This prepares the dataset for later processing and modeling. Before training the model, the code verifies that the number of feature rows matches the number of labels. This check ensures each input has a corresponding target value. If the counts differ, it raises an error to flag the dataset mismatch and prevent unreliable training. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 1/4 of the data kept for testing. Stratification preserves the original class proportions in both sets, supporting a fair evaluation. A fixed random state of 42 makes the split reproducible each time the code runs. The pipeline combines feature scaling with classification. A standard scaler normalizes the input features so they contribute more evenly, which is especially important for neural networks. The model then uses a multi-layer perceptron with one hidden layer of 12 neurons, trained for up to 300 iterations, with a fixed random state to make results reproducible. The model is first trained on labeled training data, adjusting its parameters to reduce classification error. It then predicts labels for unseen test data, and those predictions are compared with the true labels. The resulting test accuracy shows how well the model generalizes to new data. Access the trained pipeline's multi-layer perceptron classifier directly, then retrieve its recorded loss values from training. Converting these values into a NumPy array makes them easier to analyze. This loss curve shows how the model's error changed over iterations, helping reveal how training progressed. The output summarizes the model run by showing the Scikit-Learn version for reproducibility, the final training loss rounded for readability, and the test accuracy as the share of correct predictions. Together, these values give a quick check of compatibility and overall model performance. This plot shows how an MLP classification loss changes during training. A Matplotlib figure is created. Then the loss values are plotted against the training iterations with clear axis labels and a descriptive title. Displaying the plot makes it easy to visually check whether the loss decreases as training progresses. This script uses a multi-layer perceptron to classify breast cancer data into two categories: It splits the data into training and test sets, scales the features using only the training data, and trains a neural network with one hidden layer of 12 neurons. After training, it reports the final loss and test accuracy, then shows a loss curve to illustrate how the model improves over training iterations. Regression loss. A multi-layer perceptron for regression predicts continuous values rather than class labels. During training, it compares each prediction with the known target and uses the error to update its weights and biases. In Scikit-Learn's MLPRegressor, learning is guided by squared error loss, which penalizes larger mistakes more and helps move predictions closer to the true values. For multi-layer perceptrons used in regression, it is important to scale both the input features and the target values. Features with very different ranges can make learning inefficient because the network may give too much influence to larger numerical values. Scaling helps the model learn more evenly and allows the loss to decrease more smoothly. Scaling or transforming the target can also improve optimization when values are large or highly skewed. A lower regression loss means the model fits the training data better, but it does not guarantee strong performance on new data. If training loss is low, while validation results are poor, the model may be overfitting, especially in flexible models like multi-layer perceptrons. Always interpret loss together with validation scores and the real-world impact of errors, since acceptable error depends on the task. Python code, regression loss. This example trains a small multi-layer perceptron regressor and shows how scaling can help the optimizer lower regression loss. It then compares the resulting loss and test error. This setup imports tools for building and evaluating a regression model. NumPy supports numerical work, while Scikit-Learn provides functions to create synthetic regression data, split it into training and testing sets, build a neural network regressor, standardize features, and combine steps into a pipeline. The model's performance is then measured using mean squared error, which compares predicted values with actual values. We create a small regression dataset using Scikit-Learn's MakeRegression function with 500 samples and 4 features. Added noise makes the data more realistic, while a fixed random state ensures the same dataset is produced each time. This makes the setup useful for consistent model testing and comparison. To demonstrate feature scaling, we copy the feature data so the original stays unchanged, then rescale 2 columns in opposite directions. One column is multiplied by 1000 to represent a larger unit, while another is multiplied by 0.01 to represent a smaller unit. This shows how regression data can include features measured on very different scales. The code verifies that the features and target have the same number of rows, so each feature set matches one target value. If the counts differ, it raises an error to prevent misaligned data from being used during model training. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, and a fixed random state makes the split reproducible. This helps prevent test data from influencing training and gives a more reliable estimate of model performance. The model is built as a pipeline that first standardizes the input features, helping the neural network train more effectively. It then uses a multi-layer perceptron regressor with one hidden layer of 20 neurons, ReLU activation, and the Atom optimizer. Training is allowed up to 800 iterations, with a fixed random seed for reproducible results and detailed training output turned off. A model is trained by learning from the training data, adjusting its parameters to reduce the difference between its predictions and the actual target values. After training, it uses those learned patterns to make predictions on test data, which helps evaluate how well it performs on unseen examples. We retrieve the trained MLP regressor from the pipeline, then use its training loss to see how well it fit the training data. We also compute the mean squared error on the test set to measure performance on unseen data. Comparing these two values helps evaluate both training fit and generalization. The output reports key information about the model and its results. It shows the Scikit-Learn version for reproducibility, the training loss to indicate how well the neural network fit the training data, and the test mean squared error to assess performance on unseen data. It also displays the first 3 rounded predictions in an easy-to-read form. This script trains a small neural network regressor on a synthetic dataset whose features have different scales. It splits the data before applying scaling to avoid data leakage, then uses a pipeline that standardizes the features before fitting the model. After training, it reports the Scikit-Learn version, the model's training loss, the test mean squared error, and a few sample predictions. The example emphasizes why feature scaling matters in regression and shows how training loss compares with test performance. MLP prediction behavior. Backpropagation intuition. Backpropagation helps a multilayer perceptron learn by sending prediction errors backward through its layers. The loss function measures how inaccurate the prediction is, and backpropagation determines how each weight contributed to that error. This feedback guides the network in adjusting its connections so future predictions become more accurate. Backpropagation trains a neural network by sending error information backward from the output layer and using it to adjust the weights in each layer. This shows how small weight changes affect the final loss, so neurons can improve the outputs they pass forward. The output layer receives the most direct feedback, while earlier layers get filtered signals that help them learn useful features, such as edges and images that later layers combine into more complex patterns. In supervised learning, backpropagation is the feedback process that turns prediction errors into weight updates. Activation functions help the model learn nonlinear patterns, while the loss function measures how wrong its predictions are. Using this feedback, the optimizer gradually adjusts the model so it can make more accurate predictions, such as identifying patient risk levels or estimating housing prices. MLP classification. In classification, a multilayer perceptron assigns inputs to categories by passing features through hidden layers and producing class scores. These layers combine signals in nonlinear ways, allowing the model to learn intermediate patterns rather than rely on simple rules. This helps it recognize complex relationships, such as risk factors in medical screening or clues that an email is spam. In classification models, the output layer turns model scores into category predictions. For binary tasks, a score is compared with a threshold to choose between 2 classes, while multi-class models usually select the class with the highest score. These scores may resemble probabilities, but they are not guaranteed to be reliable, especially when the training data is poor. Always interpret predictions in light of data quality and context. A loss function guides a classifier by measuring how far its predictions are from the correct labels. Higher loss occurs when the model is unsure or confidently wrong, pushing it to adjust and improve. However, good training performance can be misleading if the model memorizes irrelevant patterns instead of learning what truly matters. For this reason, evaluation should look beyond accuracy to include class confusion, probability calibration, and the real impact of mistakes. Python code. MLP classification. This example trains a small multi-layer perceptron classifier and examines the probabilities behind its class predictions. It compares the model's confidence with the true labels to show how well the predictions align with the actual outcomes. This setup imports the main tools needed to build and evaluate a simple neural network classifier. It uses NumPy and Scikit-Learn, loads the iris dataset, splits the data into training and testing sets, and prepares an accuracy measure for evaluation. It also creates a pipeline that standardizes the features with a standard scaler before training a multi-layer perceptron classifier. We load the iris dataset, a small built-in dataset commonly used for multi-class classification. It is separated into input features, which are flower measurements, and target labels, which identify the iris species. This split provides the data needed to train and evaluate a machine learning model. Before training, the code verifies that the feature data and target labels have the same number of rows. This confirms that each example has a matching label, which is required for supervised learning. If they do not match, the code raises an error to prevent training on misaligned data. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 30% reserved for testing. This lets the model be evaluated on data it did not see during training. Stratifying by the target keeps the class balance the same in both sets, and setting the random state to 42. The data is prepared with a pipeline that first standardizes the features by centering them and scaling them to unit variance, helping the neural network learn from each feature fairly. The pipeline then uses a multi-layer perceptron classifier with one hidden layer of 8 neurons. Training is allowed up to 1,200 iterations, and a fixed random state of 42 makes the results reproducible. The model is first trained on the training data, where it learns patterns from the features and labels. It then uses what it learned to predict labels for unseen test examples. The model can also estimate the probability of each possible class, which shows how confident it is in its predictions. To check the model's predictions, we select a small group of examples, specifically the first 5. We then look at the predicted probabilities for those examples and round them to 2 decimal places. This makes it easier to compare the results and understand how confident the model is in each prediction. This section checks the Scikit-Learn version for reproducibility, then evaluates the model by comparing true and predicted labels to compute test accuracy. It also maps the iris dataset's numeric labels to class names, so the true and predicted results are easier to interpret. Finally, it shows the model's predicted probabilities for selected examples, giving a clear view of how confident the model is in each prediction. This script trains a small multi-layer perceptron on the iris dataset. It splits the data into stratified training and test sets, standardizes the features, and trains a model with one hidden layer of 8 neurons. After training, it reports the Scikit-Learn version, test accuracy, sample true and predicted labels, and rounded class probabilities to show the model's confidence. MLP regression. In regression tasks, a multi-layer perceptron predicts continuous values, such as prices, temperatures, or fuel efficiency, instead of class labels. Its hidden layers transform input features into internal patterns that can capture complex, nonlinear relationships. The final layer produces a numerical output, allowing predictions across the full range of the target variable, rather than limiting results to probabilities. In an MLP regressor, the loss function guides learning by measuring how far predictions are from the true target values and adjusting weights to reduce that error. Predictions close to the target are penalized less than large mistakes, so outliers can strongly affect training. To interpret performance well, prepare the data carefully by scaling inputs, checking target distributions, and comparing training results with validation results. A multi-layer perceptron regressor makes predictions by learning patterns from its training data, so its results are most reliable for inputs similar to what it has seen before. Its hidden layers can capture complex relationships, but they do not guarantee common sense or accuracy in unfamiliar situations. Always judge predictions in context by checking whether the inputs are realistic and whether the model performs consistently across different datasets. Python code, MLP, regression. This example trains a small multi-layer perceptron regressor to predict continuous values. Scaling the data helps the neural network learn more stable mappings, and its predictions are evaluated by comparing them with the true target values. This setup imports the main tools needed to build and evaluate a regression model. It uses NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning. From Scikit-Learn, it loads the diabetes dataset, splits the data into training and testing sets, scales the features, trains a neural network regressor, and evaluates performance using mean absolute error. We load Scikit-Learn's diabetes dataset, a built-in dataset for regression. It provides input features used as predictors and target values representing diabetes progression. These data are used to train and evaluate a regression model. The code first checks that the feature data and target data have the same number of entries. This ensures each set of features has a matching target value before training a regression model. If they do not match, it raises an error to prevent problems during training and evaluation. First, the dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, so the model can be evaluated on data it has not seen before. A random state of 42 makes the split reproducible. Splitting before scaling also helps prevent data leakage and avoids overly optimistic performance results. This pipeline first standardizes the input features, then trains a neural network regressor. The model uses one hidden layer with 20 neurons, a ReLU activation function, and the LBFGS optimizer, which is well suited to smaller datasets. Regularization is set to help reduce overfitting. The model is allowed up to 1,000 iterations to converge, and a fixed random state makes the results reproducible. The model is first trained on the training data by adjusting its internal parameters to reduce the gap between predicted and actual target values. After training, it makes continuous predictions on the test data, which helps evaluate how well it performs on unseen examples. The model is evaluated using mean absolute error, which shows how far its predictions are from the true values on average, regardless of direction. The Scikit-Learn version is printed to support reproducibility and debugging. The test error is then reported in disease progression units, and the first prediction is compared with the first actual value to give a quick check of model performance. Create a new Matplotlib figure and axis with a 6x5-inch canvas. Then make a scatter plot comparing the test set's true target values with the predicted values. Use slight transparency so overlapping points are easier to see, and label the points as test cases for the legend. To show perfect predictions on a plot, draw a reference line across the full range of both true and predicted values. The range starts at the lowest value found in either set and ends at the highest value found in either set. A black line through this range marks where predictions would fall if they exactly matched the true targets. The plot is finalized by adding a clear title, labeling the axes for true and predicted target values, and including a legend to identify the test points and perfect prediction reference line. It is then displayed with Matplotlib's show function, so the model's predictions can be visually compared with the true values. This script trains a multi-layer perceptron regressor on the diabetes dataset. It splits the data into training and test sets, scales the features, and fits a neural network with one hidden layer using a rectified linear activation and the LBFGS solver. After training, it predicts test values, measures accuracy with mean absolute error, compares one prediction with its true value, and uses a predicted versus actual scatter plot to show how closely the model matches the targets. In this lecture, you learn to explain the structure of Scikit-Learn MLP models in practical terms, fit MLP classifiers and regressors on scaled data, and interpret activation, loss, and prediction behavior for supervised MLPs.
Thank you for your attention. See you all in the next lecture.